everyone. Thanks for coming. So my name is Yevgeny. I came here from Tel Aviv. In this session, I'll talk about fuzzing in general, and in particular, I'll talk about Go Fuzz, and also discuss how to integrate it into your CI/CD. So a little bit about me. I'm the founder of Fuzzit. Before Fuzzit, I did a lot of consulting with focus on penetration testing, security research, and DevSecOps, DevOps. Before that, I did a couple of ventures, some VC funded, some not. And before that, I served at the cybersecurity part at IDF. So agenda, we'll discuss what is fuzzing, what we want to fuzz usually, what types of fuzzers exist. We'll discuss about Go Fuzz, because essentially this is a Go Fuzz conference. And then we'll show a demo, show some examples of how to use it. Then we'll discuss how to integrate it into your CI/CD and what usually the workflows we have with continuous fuzzing. Then we'll discuss some case studies, what fuzzing is not, what fuzzing does not replace, and the future of fuzzing, and then we'll do short Q&A. Before I start, who is familiar with fuzzing here? Okay, a few people. Who really used fuzzing in their projects? Okay, one person. And who integrated into their CI? Okay, one person. Nice. So hopefully it will be better after this talk. Okay, cool. So fuzzing essentially is a way of providing semi-random input to your test program to uncover bugs and crashes. The second questions that I get a lot is it only to find like security or memory corruption vulnerabilities? Because essentially in Go we don't have those problems because it's a safe language. So the answer is that yes, you won't find any memory corruption vulnerabilities in Go, but you will find a lot of bugs, and you will improve stability of your code. You will improve coverage, and you also might find logic bugs as well as like crashes that will lead to denial of service, and they are security bugs as well in Go and in other safe languages. And the last thing is it actually will run millions of unit tests without really writing them, which is pretty cool. So what to fuzz? So usually, like the classic examples are libraries that doing compression, decompression, like network parsers, DNS, for example. If you're a DNS provider like Cloudflare, it's classic for you to parse your DNS server, deserialization libraries, crypto libraries, and other media formats, databases. So essentially anything that gets and parse complex input, usually you will find a lot of bugs with fuzzing. Okay, so I'll talk in this session mainly about two types of fuzzers. So the traditional one, just the random fuzzer, and the coverage-guided fuzzer, which is actually it was proved to be very successful. So it started with AFL and Leaf Fuzzer for C++. They uncovered a lot of security issues and memory corruption bugs. And then they were ported to different languages. So they were ported to Go. And Go Fuzz was created, initially developed by Dmitry Vyukov. And they were ported also to the other different languages like Python Fuzz, JS Fuzz, Java Fuzz. Those ones were ported by me. So I'll go into a simple example. We have ParseComplex function in Go. It's not really complex, but just for the sake of the example, it gets a byte array. And what the function wants to do is, if it gets the word, the byte array fuzz it will return true, and otherwise it returns false. Anyone can spot the bug here? Yeah. What's the bug? Yeah, that's right. So it's classic off by one. Actually, the program will crash if it will get the byte sequence fuzzed. And now we'll try to find it with a fuzzer. So before I show you an example of how Go Fuzz finds it pretty quickly, I'll want to show you how it really works. So on the left side, you have how random fuzzers works. So they just generate completely random input, and then they feed it to the test program. And the coverage guided, they have a few more steps. They have one preliminary step. They instrument the program for coverage because they need the coverage feedback. And then they're doing, in a loop, they're doing something, they're choosing a random input from something called the corpus, which is essentially just a directory with test cases. If it's empty, just generating a random test case. Then it's mutating this input, and I'll talk about what types of mutation it's doing. Then it feeds to your test program. It collects coverage, and if it gets any new coverage, if it sees it, this test case is got the fuzzer to new coverage, new code blocks, it will add it to the corpus. We'll add it to the test case. So here are two examples of fuzzers. On the left side is a simple random fuzzer, which for some confusing reason also called Go Fuzz, just without the dash. You want to use the fuzzer Go Fuzz with a dash on the right side. So on the left side, just like I said, it generates completely random string, and then we feed it to our ParseComplex function. It will not find the bug any time, essentially, and I'll explain why. And on the right side, we have an implementation of Go Fuzz fuzzer. So you have to implement a function called Fuzz. So the fuzzer will call this function indefinitely for you with the algorithm that I showed you before, and will pass the pseudo-random data to the data variable. And then we call ParseComplex. So to run this, we need to download Go Fuzz and Go Fuzz build. I'll show you a demo in a second. We run Go Fuzz build, which essentially instrument our binary, and then we run Go Fuzz, which run this binary indefinitely and calls the fuzz function with the pseudo-random data. So the Go Fuzz finds the crash in about 2 seconds, and the random fuzzer will not find the crash because essentially the probability to find the word fuzzed out of all the strings in the world is 0. So now let's do a quick demo. 1 second. Yeah. So I have the same. I will get the example. Okay. Go Fuzz has 2 types of engines. It can run with like native Go Fuzz, or it can run with the lib fuzzer engine. In this example, we will use the lib fuzzer engine. Like, I won't dive into what's the differences, but overall it's produce similar results. So here we run the instrumentation step. It will produce a binary. And before that, we have here the ParseComplex, the code that I showed you in the slides. ParseComplex Go, and we have the fuzzer that we implemented. You can see that, yeah, it's a simple function, the fuzz function, and now we will compile it with the lib fuzzer engine. Okay, now we have the Go Fuzz fuzzer. Now we'll just run this. Okay, it found the word without any. We didn't give it any seed test cases, and it found the fuzzy word pretty quickly. It also saved this to the disk. We have the crash. So it works. And a little bit about what happened behind the scenes, apart from the algorithm. So the data generation for the random fuzzer, just like I said, is generating completely random inputs, so it will never hit the word fuzzy. And the data generation for Go Fuzz, so it's not all the test cases that were generated, but it's the test cases that were saved to the corpus. So essentially, our fuzzer will each time it won't get stuck. So it will continue exploring new edge cases and new code blocks. So first it will start with an empty string, and then it will find essentially the next character in a few iterations, and will save it to disk. So this way it will actually get to the word fuzzy pretty quickly. So we can do more sophisticated stuff with coverage-guided fuzzing. We can also find logic bugs. So for example, if we have some kind of encoder, decoder, or encrypt and decrypt functionality or library, we, for example, can call mydecode myencode data and see if it really equals to data. And this way we can find logic bugs in our library if our tests really fails. So it really works. So this is just, I think, 1/10 of the bugs that were reported, and you can find it in the GoFuzz GitHub. A lot of them are in the standard library. Some of them are not in the standard library. So it really works. About mutations, actually it's usually pretty simple. It's doing some kinds. There are about 20 mutations that you can find in also all of them in the source. It's I think one file. It's doing bit flipping, byte flipping, and some arithmetics. Also, it's using some magic numbers that the fuzzer knows that usually it leads to bugs like max int, min int, and stuff like that. There is another engine that called Sonar that I won't discuss here. It's a bit more advanced, but you can look in the repository. It's documented a little bit. Okay, so solution and what fuzzing is not. So it does not replace unit tests. You still want to have unit tests in your code. You want to have integration tests. It doesn't replace secure design or threat modeling, attack surface reduction, of course, if it's applicable to what you write, because it doesn't say if you run a fuzzer, it doesn't say that you don't have bugs. You probably still have bugs, so you need to think what is the threat modeling and what will be a good secure design to reduce your attack surface. And also as a developer, just like you write unit tests, you're also responsible for writing the fuzz tests, because you're the best person to understand what is worth fuzzing and what functionality in your code is the best place to fuzz. So continuous fuzzing. So just like running a fuzzer once probably will find bugs, but you want actually to run it every time you push new code, just like you run unit tests every time you push new code, and not once in a year, hopefully. So the problem with fuzzing is that unlike unit tests, fuzzing can run indefinitely or for a very long time. So we'll discuss how we integrate it into our CI/CD, and how long should we fuzz and what version should we fuzz. So before I dive into the continuous fuzzing workflows, so Fuzzit really focuses on helping integrate fuzzing into your CI/CD, but essentially you can use the same workflows if you have the resources to spawn it, build it yourself, or use some open source alternatives like ClusterFuzz, also if you have the time. If you want something a bit more managed, we also have a free tier for open source, so you can give it a try. So we integrated really a lot of continuous fuzzing for open source projects, like systemd, CoreDNS, and we found that those two workflows were most successful to finding and preventing new bugs. So the first workflow is fuzzing workflow. So every time you push new code to master, you build your binary fuzzers in the CI, and then you upload them to a server, to fuzz it, or to your server, where you will run them without blocking your CI, because you don't want to block your CI. And then the fuzzer will run either until it finds a crash, or until a new version of the fuzzer is uploaded. And another important thing, you have to save the corpus between the runs. So every time you upload a new version, it won't start fuzzing from the beginning. It will start fuzzing from essentially from the same place, and hopefully it will fuzz only the new code that you added to this commit. So this workflow will guarantee that your latest version is being fuzzed, and of course you will be notified of any crashes the fuzzer finds. So the second workflow is a regression workflow, and this is something that you can run inline in your CI, because in the previous workflow you generated a lot of very good test cases that get you to a lot of new coverage. Plus, also it generates crashes that you hopefully fixed. So you can take this corpus, all the crashes that you fixed, download them into your CI, and run the fuzzers through this set of test cases. So this is just like a free unit tests, and it will help you prevent old bugs that you already fixed, and also prevent new bugs that you just introduced. So some trophies just from our Twitter. I think it's good 2 examples about two use cases. So one repo is syscaller. It had fast tests written for its project, but it didn't run them continuously, and essentially, so probably ran it a few months ago, and he wrote a lot of code, and he ran the fuzz integrated continuous fuzzing, and he found some new bugs. So just like you run unit tests, you want your tests to run every time you push new code. And the other example is a package, actually a compression package that found a bug after 10 hours. So you usually don't want to run your CI for 10 hours every time. So this way, when you separate your CI from your fuzzing CI, you can run your fuzzers for a long time, essentially indefinitely, but you don't really run them indefinitely. You run them until you push new code, and then you swap the versions. So every time you only fuzz your latest version. Yeah. Okay. So the future. The second thing that we talk about in the fuzzing community is that currently a lot of the libraries only support like passing a function which gets a byte array, and then if you have some more complex functions, you usually have to implement some kind of permutations yourself to turn it into like random structs, and it will work. But we work, and there are open issues, and we work on implementing structure-aware fuzzing out of the box. So you can, for example, have this fuzz function, but you will be able to specify what types of variables you want to get. Maybe you want to get a struct of some kind, and not only a byte array. So this is one thing. And the other thing is also there is a suggestion and an open issue in Go specifically to implement it as part of the standard library. So you won't need to like go get, go fuzz, and probably some things will work smoother, but actually it is pretty stable in my opinion. Okay. Questions?
Hello, test. I have a question about you only showed unit tests. What about integration tests? How can I test for errors like does this code doesn't produce a panic, but a logic error? So I expect true, but I get false. How do you have Fuzz for this?
Yes. So I think it will be hard to implement this out of the box at least with the current library. Because the current library, not only in Go, but also in like libfuzzer and AFL, the original libraries, are usually, they are working very well when you have like one library. They're not working well when you have a service, because then you have to somehow instrument all those like microservices and generate a lot of code. So they don't really, I would say there is no easy way today doing this. So it will work if you have some kind of like library that you can somehow, or at least extract this behavior to a library, and then you can fuzz it. Okay. Thank you.